Manikandan sir.
Yes, sir. Can I start?
Yes, sir. Just I give the welcome address, sir. Then we will start. Good evening, one and all. Today, third day of AICTE sponsored Atal Faculty Development Program on Engineered Material for Multidisciplinary Applications, organized by NPR College of Engineering and Technology and Autonomous Institution, Natham, Dindakal. I extend a warm and heartfelt welcome to each one of you. It is a great privilege to have you all here for the today's session. Uh, Dr. M. Veeramanikandan is an assistant professor in the Department of Mechanical Engineering at SRM Institute of Science and Technology, Chennai. He completed his doctoral studies in the area of solar system at Anna University, Chennai, Tamil Nadu, India. Since 2016, he has been actively involved in the teaching professions throughout his academic career. Dr. Veeramanikandan has authored several research articles and books which have been published in prominent international journals and by renowned publishers. His expertise lies in the field of renewable energy, particularly solar thermal system, and he has contributed significantly to the advancement of research in this domain. We are excited to engage with our distinguished resource person, and I encourage all the participants to actively participate in this session, and I request ask questions and make the most of these opportunities to learn and grow together. Once again, I welcome you all to this FDP session and look forward to a fruitful and enriched experience. Thank you. Um, Dr. M. Veeramanigan, sir, the forum is yours. Please, sir.
Thank you, sir. So,
Yes,
good
sir.
evening to all. So, I'm welcoming you all to the third day of the faculty development program on engineering materials for a multidisciplinary application. First and foremost, I wish to convey my gratitude to Dr. C. Manival sir and his team, and the Department of Mechanical Engineering and the management of NPR College of Engineering and Technology for providing this opportunity. So the topic is assigned to me is trends and application of thermal material and manufacturing technologies. So in this session, I'm going to discuss the topics with you all: trends in thermal material and technologies, application of thermal materials and technologies, high performance materials for the energy conversion, emerging trends in energy conversion materials, advancing solar energy utilizing perovskite material for enhancing photovoltaic efficiency, then perovskite solar cells materials technologies, and finally application and features of perovskite solar photovoltaic technology. So, Manimal sir already gave an introduction about me. So actually, I'm doing my research in solar photovoltaic thermal system. So it is a combination of electrical and thermal system. So I have a knowledge in solar photovoltaic thermal system. So in this session, I'm going to explain about the thermal materials, and finally, I'm going to discuss. I'm going to share my knowledge about the recent research is done in are going in the area of perovskite solar cells. You know very well. We are all are using the multi polycrystalline solar photovoltaic cell, which is available. The silicon photovoltaic cell, which is available in the market. You know very well. But nowadays, the research is going on the peroxide solar cells because it is very cost effective and efficient. So most of the faculties and the researchers that doesn't have idea about peroxide solar materials. So first, I will explain about the thermal materials and its impacts and its application. And later we will discuss about the perovskite solar material. Okay. So, very well, sir. Is my voice is audible? Is my
Sir,
voice audible?
yes, sir. Yes, yes. Sir,
Okay, thank you.
please change presentations mode in the slides.
Okay, okay, thank you.
Yes. Thank you. Good, sir. Thank you.
Okay, great, sir. Actually, so first we will discuss about the various trends and technologies used in thermal material. So nowadays, thermal materials are used in various areas in various field forms. So first, it is used as an advanced thermal interface material. So nowadays, thermal materials are used as a interface material for extracting the heat from high temperature area by improving the thermal conductivity and reliability. You know very well. The thermal material means which has a high thermophysical capacity. Okay. If it is having a high thermal characteristics, it is vice versa. It is directly proportional to the electrical characteristics. Okay. You know very well. For example, if you are taking copper as a thermal material, it has a good thermal conductivity as well as it has a good electrical conductivity. So almost those metals having has the high thermal or thermophysical properties, which is also having a electrical properties. Okay. So in nowadays, thermal materials is used in interface material we already discussed. In general, graphene-based and phase change carbon nanotube enhanced materials are the best example for the thermal interface materials. These thermal interface materials is generally used for electronic cooling like CPU or GPU. GPU means graphic processing unit and the power modules. So these thermal interface materials are used for cooling purposes for the particularly for the electronic items. Okay. And second, in general, it is used as a lightweight and high strength material. And in general, carbon fiber reinforced polymers are used as a composite materials, and aluminium and magnesium alloys used as a lightweight material in current days. Okay, so these materials has a high thermal physical characteristics, high strength, and light in weight. Okay, so these lightweight and high strength thermal materials is commonly used in aerospace and automotive components for thermal management. And it is used in the area of 3D printing or additive manufacturing. And, in current scenario, the thermal materials are used in 3D printing and additive manufacturing process. You know, when the additive manufacturing and 3D printing is nowadays in the emerging area. So advances in 3D printing allow for customized thermal components with complex geometrics such as heat exchanger or cooling things. So where we are where the heat is occur or suppressed in the complex structures like the heat exchanger or cooling fin. In this area, we can developing the area using 3D printing or additive manufacturing. So these are generally used for rapid prototyping, aerospace components, and medical devices. Okay. So the most commonly used high temperature materials in 3D printing are flame retardant resistance, rigid 10K resin, silicon 4A resin, and aluminum 4N resin. These are all the most commonly used high temperature materials in 3D printing and additive manufacturing. And in the nanotechnology area, integration of nanomaterials such as nanofluid or nanostructures. Okay, we can use either nanoparticle in the base material or we can develop as a nanofluid. That means the nanoparticle is mixed with the base fluid. It is called nano fluid. Or in the nanostructures like the carbon nanotube. So these are all the nowadays we are using the thermal materials in this form like nanoparticle, nanofluids, and nanostructures. So, these are to enhance the thermal conductivity and heat dissipation. For example, copper oxide, aluminum, and titanium and gold particles are generally blended and coated on the base material to enhance its thermal performance. So the nowadays the people who are doing thermal research using the nano application, the nano technology, so the most of all we are using the copper oxide or aluminum oxide or the tungsten, so which having a high thermal conductivity, and also which is used to increase the strength and possibility to augment the other characteristics like ductility or the um, what I think, ductility, strength, thermal conductivity, or something like that. So these materials, these thermal materials with nanotechnology are used for electrical cooling, energy storage, and solar thermal systems. Okay? So we are using the nanomaterial for the water collector and the phase change material, the solar thermal system like evaporative tube collector or a flat plate collector. So nowadays we are mixing the nanoparticle with the base fluid like water or any other fluids, or we can use as used in a heat exchanger fluid. So nowadays, the thermal materials gives like a greater impact in the nano area. And the phase change material, phase change material is one of the best example for the high thermal materials. Okay, because which has which because it stores the heat as a latent heat. Okay, we know very well the difference between the latent heat and the sensitive heat. So the latent heat means which contains high amount of thermal energy with itself. So, but the remaining solid thermal materials are absorbed and liberate the heat as a sensitivity. So, the phase change materials give a vital role in thermal applications. So, use of PCM or for phase change material for energy storage and thermal regulation, including the bio-based and encapsulated PCM for improved efficiency and environmental compatibility. Okay. So these phase change materials are generally used for building insulation, thermal energy storage, and temperature sensitive logistics. Okay, and I can use in the um, thermal materials in a sustainable and, as a sustainable and recyclable material. So the focus on the eco-friendly material that offer the management properties while minimizing the environmental impacts. And generally, it is used in the green building materials. The sustainable materials like are used in the green building materials and sustainable package solution. In nature, the natural recyclable the sustainable materials such as stone, concrete, or bricks. Okay, so we can, for example, if you're using the sustainable in a greenhouse mean, we can introducing the solar PV windows as a so we can fix the solar PV as a window in our greenhouse in our eco-friendly manner. Okay, and last, in advanced manufacturing, it is used in the advanced manufacturing process. The use of these techniques like injection molding, advanced brazing, and robotics assembly to produce thermal management components with the precision and scalability. It is generally used for high volume production of heat sinks, for thermal pads, and cooling models. So these are all the current trends in the thermal materials and technologies. Um, and the application of thermal materials and technology. So generally, the thermal materials are used in the most multidisciplinary areas like electrical, electronic, biomedical, and civil water. And in all disciplinary areas, nowadays we are using the thermal material because we need to. And in some places we need heat. At the place we can use thermal material as a storage medium. In some cases we need to extract the heat from the system. In that cases we can use the thermal material to extract the heat. For example, in the engine, we need to remove the excess heat from the engine. If it is heat is increasing in the engine will collapse. That means the body will be the property of the body will be reduced. Okay. For example, in the solar water heater, we need to extract the heat from the subfracted collector. So in this case, we are using the high thermal materials like copper and aluminum to extract the heat from that. So based on the application, based on the area, we can use the thermal materials as a heat absorber or a heat emitter. Okay. The first is the thermal materials used for efficient heat dissipation in microprocessor, LED, and power electronics, in the electronic and semiconductor industries. Also used in advanced thermal insulating materials in the heat pipe and vacuum chamber, upper chambers. And second thing, it is used in the renewable energy. So we know very well nowadays the thermal materials are used in the solar water heater, solar air heater, solar plant, what else? The very in many areas, not only solar, in the wind, tidal, whatever the, and then in more renewable energy areas, we are using the thermal materials because the heat energy is mainly used to convert used to convert used to generate the electricity or they can be used as a process heat. Okay. In the renewable energy area, the thermal storage material is concentrated in solar power system, concentrated solar power collector. So advanced coatings for photovoltaic panels to manage the heat. Okay, so in order to maintain the heat, they are applying the high temperature materials or the reflecting materials on the solar photovoltaic top surface of the solar photovoltaic panel. Okay. In the automotive or AV area, it is used in battery thermal management system to enhance the performance and safety. And also is used as a heat resistant material for engines and exhaust systems. In the aerospace area, lightweight thermal insulation materials like aluminum or tungsten like that are using for a spacecraft and aircraft. And high temperature metals for the turbine blades and heat sinks. Okay. We can use the high temperature metals for to design or to manufacturing the engines and the exhaust system of the aerospace or the aircraft. Okay. In the area of healthcare and biomedical, we are using the high temperature materials in the MRI scans and the PCM based solution for the vaccine or transport. This is for used for the PCM based storage, which is used for the vaccine transport and thermal sensitive drugs. Okay. So uh, we can preserve the drugs, okay, with the help of high thermal materials. And in the area of constructive and infrastructures, the thermal insulation materials in a building for the energy efficiency. Okay. So nowadays, the building integrated photovoltaic thermal systems are used, used in a constructive field. So it is act as a insulation material as well as it is used to generate electricity to the house purpose. Okay. And PCM enabled wall panels are roofing system for temperature control. Yes. So the cooling, the building cooling is classified into active cooling and passive cooling. So in this passive cooling, so we can use the the PCM as a PCM enhanced wall panel as a uh, thermal barrier medium. Okay. And next is high performance material for energy conversion. We will discuss what are the high performance materials are used in the energy conversion area. So because I'm from the energy background, so I wish to discuss about the energy conversion area. The first one is a perovskite material. So it has a high light absorbing and charge carrying characteristics, and it has tunable band gap for tailored applications. Okay, the band gap is the main the important thing in the photovoltaic model because the band gap is increasing. It will give the conversion of positive and negative and the generation of electricity will be comparatively high. Okay, and so in this for perovskite materials, we can tune the band gap, okay, in the tailored applications. Okay, it is mainly used for the solar cells, light emitting diodes, and the thermal electrics. Okay, the major advantage is that the tandem solar cells combining the perovskite with the silicon. Okay, we can use this for perovskite materials with the silicon. Okay, we can use as a separate photovoltaic cell, or as we can use as a with the silicon. And stability enhancement through the encapsulation. That means it gives a better stability through encapsulation and composition layer. And in the area of thermal materials, and the materials like bismuth telluride, lead telluride, and silicon germanium, which are most used, these materials are used as used in the thermal electric materials. Okay, so which are used in the waste heat recovery, cooling devices, and wearable electronic devices. So because which have a high Seebeck coefficient, with a low thermal conductivity and high electrical conductivity. So it's, the main advantage is the current research in this area is the nano structuring and doping the enhanced thermal because of weight, figure of weight. Okay, so these are all the applications of the thermoelectric materials. The third one is the piezoelectric material. The piezoelectric material, the lead zirconite and the barium titanite and the polymer-based materials like PVDF. Sorry, okay, because which is used to convert the mechanical energy into electrical energy. You know very well about the piezoelectric material with a high efficiency. So it is generally used in the energy harvesting sensors and the actuators. But the recent advancement in the piezoelectric material, high temperature materials is the development of lead-free and flexible piezoelectric material. Because nowadays we should, the government is encouraging us to use the resources as a sustainable way. So we and the piezoelectric material, the advancement is they are developing lead-free and flexible piezoelectric material. And a solid oxide material. Nowadays, the iridium stabilized zirconia. The most of the researchers are used with this material in thermal barrier coating. So these iridium stabilized zirconia and the gadolinium Syria and the lanthanum strontium, cobalt ferrite. These are all the best examples for the solid oxide materials. So which are generally used in the solar oxide fuel cells for electric generation. So, because which has a high ionic conductivity and chemical stability in the elevated temperature. The advancement in this solar oxide material research is the lowering operating temperature for improved durability and cost effectiveness. Okay, because the fuel nowadays the best alternative for the battery is the fuel cell, so which is still in under research. So the our high thermal materials is plays a vital role in the uh, developing the fuel cells. And then catalytic materials, the catalytic materials like the platinum group materials, platinum, palladium, like the transition metal oxides and the metallic iron frameworks, which have in the high catalytic activity and the stability for the energy conversion reactions. So, which are generally used in the hydrogen production, fuel cells, and chemical energy storage. You know, very well the catalytic agent. The purpose of catalytic agent is which is used to boost the process. Okay. So nowadays, not only developing the fuel cell, so to boost the chemical process, we can use the thermal material as a catalytic material. So the advancement in the catalytic materials is the development of non-precious metal catalytics and the hybrid nanostructures, which is used for cost reduction purpose. Okay. And the phase change material. Well, very well, we already discussed the basic material. It is the best high thermal material. So the paraffin wax, we generally use the paraffin wax, okay, because it is very cheap and easily available. Okay, so the paraffin waxes are hydrated salt in the bio-based PCMs, so which are generally used as a patient material. So which are which having a high latent we have discussed which having high latent heat storage capacity with the thermal reliability. Okay, it absorbs more amount of heat by itself, it vibrates slowly the heat. Okay, we can use the heat later. Okay, so we can collect the heat like a battery. So we can collect the heat when the sun is available and when the heat is available, and we can later we can utilizing the heat energy for fast heating or for the purpose of converting the electricity. Okay, which is generally used for thermal energy storage in the solar power plant and building. Okay, we already in the PCM phased water we already discussed in the previous slides. Okay, now main advancements in the PCM material is the micro encapsulation, that means there is a fixed with the PCM materials are encapsulated with any other third material, like for example the copper. Okay, nowadays my students did one research. They are for observing the more amount of heat. They are um, they're creating the copper tube. They 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 were cut the copper tube in small pieces, and they feed the paraffin waxes and they enclose this that tube like it is look like a capsule. Okay, so they are just apply this capsule in the solar water heater. So during the daytime it absorbs more amount of heat. So and in the night time it will uh, then the capsules containing the PCM which liberate the heat. So we can obtain more amount of heat energy during the night time. It's the best example for wastage material as energy storage purpose. So this is micro encapsulations and the composite material for improved thermal conductivity. And graphene, 2D materials, graphene is nothing but a carbon. Carbon has a high thermal conductivity. So which has exponential electrical conductivity and then it's a mechanical strength, okay, and the thermal stability. So it is generally used in the supercapacitors, batteries, and the flexible energy devices. And the current advancement in the graphene area is functionalist graphene for the enhanced energy storage capacity. Because most of us when the graphene is used in the battery. So nowadays the research is going on the functionalist graphene for high energy storage capacity. And wide gap, wide band gap semiconductor. We already discussed about the band gap of the semiconducting materials plays a vital role because it is directly proportional to the electrical efficiency or the photovoltaic efficiency. So generally, the silicon carbide and the gallium nitride are used as band gap materials, semiconductors, which are used in the power electronics or the high frequency energy conversion area because it has a high thermal conductivity and the breakdown voltage and switching speed. Okay, so nowadays the advancement in the wide gap semiconductors is the integration into a high efficient inverters and the power systems and the organic photovoltaic materials available. So nowadays instead of replacing the um, for example, the monocrystal and polycrystal materials. In the last 10 years, the most institutions are doing the project in the organic photovoltaic material, but still it is in, under research. Okay, so the conjugated polymers and the fluorine derivatives are generally used as organic materials because which is flexible and lightweight, which can be used in the flexible and lightweight solar panels. Okay. The main drawback in the commercial solar panel, that means the monocrystal and polycrystal solar panel is that we cannot manufacture that PV panel as a flexible, and also we cannot convert it as a lightweight photovoltaic panel. Okay. Because in the EV, in the solar assisted vehicles nowadays, if it is if the solar cells in a flexible manner, mean we can paste the solar panel in the car roof. Okay. Otherwise, if you want to fix our commercial PV panel, we need to fix the additional setup to fix the panel. So that is not good. That does not give a good look to the car. Okay. So nowadays they are using the flexible and lightweight solar panels. So that only the in the future steps we will discuss about the peroxide solar cells. Okay. And the materials, the conjugated polymers and the fluorine derivatives are used as a organic photovoltaic. So which has a lightweight and solution processable and it is mechanically flexible. So the advancements in the organic photovoltaic systems, efficiency improvements through molecular vision. Okay, because the organic photovoltaic it is developed by the molecules. The molecules extracted from the different materials. Okay, and tandem architectures and advanced ceramic compounds. So the thermal materials are used in the ceramic compounds because It has a high thermal stability and thermal shock resistance and low thermal conductivity. So it's generally used in the thermal barrier coating, turbine, and nuclear energy systems. Because in general, the ceramic and the composite high thermal materials used in used in our market are zirconia-based ceramics, silicon carbides, and carbon fiber reinforced composites. So nowadays we are developing the ceramic components for the for the precision, that means for the shining, for the exact profile, and also for minimizing cost. We can develop the product using the additive manufacturing. So, so this is my area. So the advancing solar energy utilizing peroxide materials for energy for opportunity. So we know very well. Nowadays we are using the silicon. Actually, that means the polycrystalline photovoltaic thermal system in general, which is available in market. Okay. So photovoltaic thermal systems are generally available in monocrystalline, polycrystalline. So these are made by the silicons. Okay. The silicon is a semiconducting material. Okay. But we are using nowadays the research is going on the peroxide material. That means peroxide solar cells. Okay. So what is the problem existing available in the existing solar cells? Gopi sir, can you mute your audio, sir? It is a big disturbance to it. That's it.
நான் அவ்வளோ இருக்கானா என்னண்ணா
Gopi sir, okay, thank you, sir. Okay. So, so before that, the energy conversion materials are used in different forms, like in the hybrid. It is used as the hybrid materials. That means combining organic and inorganic materials for multifunctional purpose. And it is also used as a sustainable materials, focus on the recyclable and bio-based and non-toxic materials. And also which is used in nano engineering. We already discussed about we convert that high thermal material into a nano form or the nanoparticle or nanofluid, and we can apply wherever we need to improve the property of the base material. And this integration means the development of material that enable integrated energy system, for example, energy harvesting and storage in a single device. Okay, but you can ask, sir, what is the problem in the existing solar panel? Like, means, we because we are all using the silicon. That means polycrystalline photovoltaic panel in our home. Okay, so you may ask, sir, what is the problem in the policy? First one is a main is a high manufacturing cost because the silicon requires energy intensive processes like close products, crystal growth, and the high temperature doping. And the main impact is this process, okay, increases the cost per watt. And the cost per watt means in commercially per watt solar polycrystalline panel is around 45 to 50 rupees. Okay. So when we are preparing the other material, it is comparatively very cheap. So this is the main problem. High manufacturing cost in the silicon photovoltaic panel. And the material usage in the kind of material usage, the silicon wafers need to thick means around 150 to 200 micrometers to absorb sufficient sunlight and leading to the higher material consumption. Okay, but if you are increasing the thickness of the solar PV panel, which impacts increasing the cost and waste during the wafer slicing. Okay, so because the silicon panel, solar panel, we need to increase thickness of the solar PV panel. Okay. And in the point of the efficiency limits, okay, there's a in general the maximum efficiency of the polycrystalline photovoltaic panel is 30%. Okay. Actually, in the problem in the photovoltaic thermal is um, heat. Okay, temperature is a problem. Okay, in general, if the panel reaches above the ambient temperature, okay, actually the maximum efficiency from the solar photovoltaic panel is 13% only. Okay, if 100% of heat is fall on the photovoltaic model, it will convert only 30% of heat into electricity, and the remaining 77% will be as a waste heat. Okay. But in the problem in the solar photovoltaic, if the temperature of the PV panel is increasing above the ambient temperature, there is a 0.5 percentage of efficiency drop for each degree of rising temperature. Okay. If the panel is overheating, the, the efficiency is automatically decreasing. Okay. So it then in general cases it gives a maximum 13% of efficiency. So it is difficult to extract the heat from the existing solar panel because the bottom layer of the existing panel is a triglav, which is an insulator. So it is a typical task to extract the heat from the existing PV panel. And the rigid and heavy design, yes, you know very well. This existing solar PV panel, the polycrystalline solar PV panel is very rigid and the design here. Okay, that means it is a brittle, limiting their application in a flexible and portable concept because it is available in a specific dimensions only. Okay, so based on the number of cells, only they provide only a few dimensions of the solar PV panel. Okay, we cannot convert to our required form. Okay, in the commercial PV panel. So, but the impact is missed opportunities in emerging applications like wearable electronics or in the building integrated power plants. In these areas, we cannot apply the solar more polycrystalline silicon photovoltaic models. Okay. And the point of environmental acts, environmental impacts, the production of silicon involves significant energy use and chemical waste. That means the impact is it provides a carbon footprint and environmental concerns during the manufacturing. And also, the main problem is the limited performance in low light conditions. Because, you know, if the sky is in a cloudy state, okay, in this time we cannot expect the high energy conversion from solar to existing applications, commercial PV panel. Okay, because, so the integrating into the high efficiency inverters and the power systems is a major impact. Okay, so when the light condition is poor, so we cannot get we cannot able to get any more amount of electricity from the solar PV panel. Okay, so that's all. So these are the problems faced in the existing solar cell materials. So those are the high manufacturing costs, so material usage, efficiency limits, and their design and environmental impact and limited performance. Because the environmental impact, in the point of view, the silicon is uh, taken as a chemical waste. Okay, so once we cannot use the silicon, this is a bit difficult. Okay, it is considered as a chemical waste. Okay, so the current research area in the solar PV panel is a perovskite material. Okay, which is um, under research in the US. Okay, you know the perovskite materials is nothing but a combination of minerals. Okay, which is generally in yellow or a brown color. It is a combination of minerals like calcium and titanium. Okay, okay. So it's a general formula is the ABX3EC. This is the organic formula of the perovskite. So the A represents it is a organic or inorganic situations. Maybe it is a methyl ammonium or a cesium. Okay, it may be a organic or inorganic. Okay, so this is not a material. It is a combination of minerals. The perovskite is a combination of metals. Okay, and B is a metal cation. It can be a lead or tin. Okay, so the lead is a major problem. Okay, in this perovskite and halide anion. X means the halide anion. This may be a chloride, a bromide, or iodide. Okay. So these materials exhibits a remarkable electronic properties making them the ideal for solar energy application. So we already discussed why we are, we are, what are the problems are faced in the existing in the commercial photovoltaic model. So now you can ask why we can use the Pro sheet material used in solar cell. Is there any specific advantages? Means yes, we have six advantages. First one is superior light absorption. Okay. The first one that means these composite materials have a high absorption coefficient. Okay, so high absorption coefficients enabling them to capture the sunlight efficiently with very thin films. Okay, with very thin films. Okay, but in the but in the silicon, the commercial PV panel, silicon requires thicker wafers. Okay, we already discussed it, which is used to absorb more amount of heat. Okay, so the wafers, if in the perovskite need not thicker wafer. It, it is in a thin form. Okay. But in the silicon, it needs a thicker wafer, so it will drastically uh, consuming the more amount of material and cost. Okay. The second one is a tunable band gap. So in the perovskite material, I already discussed band gap is a major thing. Band gap is a vital plays a vital role in the photovoltaic energy conversion. So in the silicon, the existing silicon, the band gap is 1.1 electron volt. But in the perovskite, the silicon is very small, 1.5 to 2.3 electron volt. This is the depending upon the combination of minerals. Okay, we already discussed it. Maybe organic or inorganic, but also. Okay. So the that point of view, high efficiency. Yes, in the conventional photovoltaic model, and we already discussed, it gives maximum 13% efficiency. But in the perovskite, if you are using perovskite material in the solar cell, it will it will give the efficiency up to 25.7%. Okay, subject in the recent research. Okay, sorry. Okay, and also the low cost material. So compared to the silicon intensity, it is comparably low cost because it can be manufactured using a spin coating or flat die coating. Okay. But in the silicon lamination, it has a high temperature crystal growth process is used for wafer slicing and it will increasing the cost. The point of view is weight and flexibility. We already discussed the commercial PV panel is available in the standard design and standard structure. Okay. But in the we can produce the power sheet solar cells in the lightweight and our required flexibility design. Okay. And the last one is the compatibility and tandem architecture. Yes, the silicon is not easily tunable for the tandem configuration. Yes, we know very well. Okay, we cannot place the silicon cell in the car roof. Okay, but we can fix the power sheet solar cells in the car roof. We can it is a we can flexible. We can fix it in anywhere. Okay. The power sheets can be stacked with the silicon or other materials. Okay, you can use either the perovskite material as is a separate material, or we can combine with the solar PV panel. Okay, so the materials in the tandem solar cells, which is boosting efficiency beyond the single junction limits. Okay. In the commercial PV panel, we are using the single junction limits. But beyond the single junction limits, we can boost the efficiency by using the perovskite materials. Okay. Next, perovskite material solar cells manufacturing technology. Okay. So we can uh, manufacturing the perovskite solar cell in a multiple way. Okay, because it is extracted from the minerals, it's a combination of minerals. We can use in the thin film deposition technique, vapor-based deposition techniques, roll-to-roll manufacturing process, blade coating, and thermal photonic annealing. In the thermal film deposition coating, we can synthesize the perovskite materials using a spin coating. Okay. It means a small amount of perovskite uses precursor solutions is deposited on the spinning substance to create a uniform thin film. In this spin coating, the main advantage is it is simple and widely used for lab scale fabrication. Okay. But it have a high control over film thickness and uniformity. Okay, the overfilm thickness is high in the commercial PV panel. So here we can control the overfilm thickness and maintain the uniformity. But the challenges in the spin coating are limited scalability for large area production test because it is very thin, so we can produce in the limited scalability. And the material wastage during the spinning process is because during spinning process there is a possibility for material wastage. Okay, so this is the challenge faced in the spin coating. And second one is the manufacturing and very technologies in spray coating. Spray coating. A spray nozzle atomize the oversight precursor solution and deposit on the substrate. This is done in the spray coating. The main advantages in the spray coating is scalable for large area substrates and compatible with the flexible curved surface. But in the challenges while synthesizing the composite solar cell materials in the solar die in the spray coating, it requires optimization to achieve uniform film thickness and stability. Okay. So this is a bigger challenge. Bigger challenge. And when you are synthesizing the composite material in the slot die coating, the continuous flow of perovskite solution is deposited onto the moving substrate to a slot die. So it is pouring in the slot die. So the power solution is deposited on the slot. Okay. So the advantages in this synthesis method, the scalable and compatible with roll-to-roll process. Okay, the first is the advantage. And the second advantage is high material utilization and uniform film deposition. Is in the slot die coating. So which is generally used for the large scale manufacturing. Okay. That one is the inkjet printing, the last machine printing in the thin film deposition technique. And the inkjet printers precisely and deposit the droplets of the perovskite solutions on the substrate, which one is on the base materials. Okay. So the main advantages in synthesizing the perovskite material in the inkjet printing is there is a high material utilization and minimal waste. Okay, the material utilization is high and waste is minimal because we know very well instead of the inkjet means we know in the commercial printing and the inkjet printing the performance of the inkjet printing is high because it consumes very minimal resources. Okay. So like that consumes very minimal the perovskite solar perovskite materials. Okay, during synthesis process. But the challenges in the inkjet printing process, it requires optimization for droplet controls and drying dynamics. This is the challenges faced in the inkjet printing. Okay. And the second method is a vapor-based deposition techniques. So we can synthesize the material using a thermal evaporation method or a vapor assist solution process. In the thermal evaporation method, the peroxide solutions are evaporated under the vacuum. Okay, so the materials are evaporated under the vacuum and deposited as a thin film. Okay, finally, all the materials are evaporated. Okay, and that means the fluid contents are evaporated, and finally the uh, minerals are deposited as a layer in the thermal evaporation techniques. Okay. Okay. In this method, the main advantage is it produces highly uniform and free from pinholes. Pinhole tools. There is no possibility for pinholes, and the uniformity is high. Okay. And the second advantage is limited scalability. So there's a suitable, it is suitable for tandem solar system. Okay. Can apply these techniques in the tandem solar system. And the challenges faced during the thermal evaporation techniques, the high equipment cost and the complex operations. So this is the equipment cost is high, but then is the operation cost is high. and it is a complex operation. Okay, it should be very precise. Okay, if anything happen, we cannot get the exact output. Okay, and the vapor associated solution process. Okay, and the solution process is that the peroxide layer is exposed to a vapor containing additional precursors for the crystallization in this method. Okay, the advantages in the vapor assisted solar solution processes enhanced film quality and uniformity. In this process also, so the vapor-based deposition techniques, the two methods gives the film quality and uniformity, and but in the and also reduce the defect density. And but this vapor assisted solution process is generally often used for improving the film properties in the lab scale production. Okay. Um, um, Third method is a roll-to-roll manufacturing. The roll-to-roll manufacturing is nothing but the continuous deposition of sheet materials or the layers on a flexible substrates. Okay, using a technique like a slot die coating or spray coating. Okay, it means a continuous deposition of the material on the substrates using the techniques like spray coating or slot die coating. So this is done in the roll-to-roll manufacturing process. Okay, and 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 the advantages in the roll-to-roll manufacturing process, there's a high throughput and a lower the production cost is very minimal. And also it is ideal for flexible and lightweight solar models. So the roll-to-roll method is used for the flexible solar cell. Okay, we can uh, bend it in any angle. And the challenges faced during the roll-to-roll manufacturing process. It requires a precise control over a layer uniformity and crystallization. Okay. So the integration of multiple layers, uh, like the electrode transport layers, in a continuous process. Okay, so it's the integration of multiple layers in a continuous process. Okay, and the fourth method is the blade coating. So in the blade coating, a blade spreads the peroxide precursor solution across the substrate, forming a uniform thin it's like a braid, look like a mixie. So it spreads the materials all over the across the substrate. Okay. But in this blade coating techniques, the main advantage is a simple and scalable for large area production. Okay. You can use a large area production and can produce large area materials. But low material waste and high deposition control can happen in this techniques. Okay. So the material waste is very minimal. So the resource utilization is high in the blade coating. Okay. This blade coating is generally used for pilot scale manufacturing technology. Okay. And the last technique for synthesis in the co-oxide sources is a thermal and a photonic annealing. Okay. So thermal and photonic annealing. The post deposition treatment method is the post deposition treatment method to improve crystalline and phase purity of the co-oxide films. Okay. There are two methods followed in the thermal photonic annealing method. First one is a thermal annealing, second one is a photonic annealing. Okay. So in the thermal annealing, heating the film at a controlled temperature. Okay. But in the photonic annealing, use the intense light source to rapidly heat the film. Okay. So in thermal annealing, I can use the heat, that is conventional heat, okay, so which is it may be generated by the furnace or generated by the electrical component, or it is passive heating. Okay, so this heat is used to heat the film. Okay, the controlled temperature. But in the photonic annealing, we can heat the film with the help of light waves. Okay, but in the advantages, okay, when you are melting this the peroxide material, the layer will be created. So the main advantages in the thermal and photonic annealing process is that it enhances the film quality and device performance. Okay. But it is a bit costlier. And the photonic annealing allows the fast processing. So this process is very fast. Okay, because we are using the light energy instead of the instead of passive heat energy, we are using the light energy to produce the heat. So the reason and our next topic is recent research in coaxial solar cells. Okay, from 2024, in the last 4 years, the U.S. government gives importance to do the research in the coaxial solar cells. This is the future of PV photovoltaic cells. Okay. So the recent research from 2021 to 24 has a significant advancements on the field of coaxial solar cells, focusing on the enhancing efficiency, stability, scalability, and commercial viability. So the key developments include in the photovoltaic coaxial solar cells are the first one is the efficient improvement. The efficient improvement. The first one is a tandem solar cell. Second one is the lead thin solar cell. So the in the research, uh, I will open this image. In this research, on this, the tandem solar cells. Okay, the Q cells, it is called Q cells, says technology. Breakthrough could reduce the space need for solar panels. Okay, so these Q cells company are developing the doing the research on the uh, peroxide solar cells. Okay, the main aim is the break through the reduced space need for solar panels. Okay, this is a current research. Okay, so in this area, the Q cells achieved 28.6% of efficiency. Okay, in large area silicon solar cell topped with the peroxide layer. Okay, because this is a well record and highlighting the potential of the tandem configuration to reduce the space requirement for the solar installation. So the tandem solar cells, which is done by the, it is developed by the Q-Cells company. So they produce 28.6 percentage of efficiency, which is a well record. Okay, this is a remarkable one. And the second thing is the uh, lead-thin peroxides. Okay, so lead-thin peroxides. I will share the material. Once include. So the peroxide research boosts solar cell efficiency and the product life. This is a topic. This is science news. So these researchers developed lead-tin peroxide solar cells with the power conversion efficiency exceeding 23%. So in this research, it is obtained that they found it is a 23% of power conversion efficiency. Okay. So in the last tandem solar cell, they provide 28.6. Okay, but here in this lead-tin peroxide material, they are producing 23% of power efficiency control. This is also the best outcome. Okay. But in the main problem in the lead method is that lead is a toxic one, so we cannot reuse it. This is not a sustainable material. So this is a major problem in the lead peroxide material. And and the stability enhancement, the point of stability enhancement, they are using their protective coating. So protective coating is done by using peroxide material. Okay, the peroxide material is used as a coating in the solar PV panel. The stability of peroxide sources tripled with the protective coating. They are introducing the triple protective coating. So, sure, the in this study demonstrates that applying a tailored protective coating can triple the operational stability of the PSC and addressing one of the primary challenges hindering their commercial adoption. Okay, and the point of outdoor durability. Okay, these are all the current research is uh, doing using the peroxide or peroxide peroxide material in the solar cell. Okay. In the point of outdoor durability, so escaping the lab into the sunlight, the research examined the durable of outdoor peroxide solar cell. Okay, can you see this image? So this is the outdoor material. The peroxide materials are used as this is a peroxide solar cell. So these peroxide solar cell are used as outdoor material. Okay, so this is used for a for it gives a better durability. Okay, escaping the lab into the sunlight. Okay. So here, the U.S. Department of Energy funded research examines the PSC degradation mechanism under real world conditions, providing insights essential for the improving outdoor durability in this area. And in the scalable manufacturing techniques, the hybrid deposition process recently used for developing the perovskite solar cells. Okay. So this is a triple cation perovskite solar cells fabricated by the hybrid PVD blade coating process. Okay, this perovskite solar cells is done by the we already discussed about the blade coating process. Okay, using the green solvents. Okay, they are using the green solvents. So the innovations in combining vapor and the solution-based techniques have facilitated the production of uniform peroxide films on a large area substrates without using the toxic solvents. Without using the toxic solvents, advanced scalable. Okay. This is the result in the triple cation peroxide solar cell. Okay, and then the commercial efforts, this means the consumer product. So we can use, they can develop the O6 solar cell as a consumer product. This also is current research. Okay. So the anchor solar umbrella used to do next generation will use as a logo. Okay. So they are used as a consumer product. Okay. For example, we can bring this solar panel wherever we go. So we can use this as an umbrella. Meanwhile, it is generating the electricity. So this is also a latest invention in the peroxide solar using this peroxide solar. So the Anchor the Anchor company names Anchor is introducing the solid solar beach umbrella equipped with the next generation peroxide solar cells capable of producing the 100 watt. So it is producing the 100. It is a 100 watt panel. So showcasing integrating the PSCs to the consumer products. Okay, we can bring anywhere to this umbrella. This is a consumer product. And so the peroxide research direction, the final research direction, which is uh, enforced by the U.S. government. Okay, these are all the current research done in the peroxide research direction. This is the peroxide research direction. Okay, so this SU has identified the four primary challenges that must be stimulated to address for the peroxide technology to be commercially successful. It means the U.S. Department of Energy outlined key area. Right. That means, and the research direction begins. The U.S. Department of Energy supplied a key area for the PSC research, emphasizing the need to address the stability issues related to the moisture. Okay, because the stability, the when you are using the proxy solar cells, the main parameters which affect the performance of the PV panels are moisture, oxygen, light, and heat exposure. Okay, so they are addressing the stability issues like a moisture, oxygen, light, and heat exposure to realize their full potential. So these are all the current research is done in the from 2001 to 2004 using the composite solar cell materials. So these researches are done in IUS. Okay, and advancement in peroxide solar cells. So this is it can be used for a efficient improvement. Yes, we already discussed. So it gives the efficiency up to 25.7% in the laboratory conditions. Okay, but not in the commercial condition. It is the Q cell is we already discussed the Q cell is generating 25.7% of the efficiency, but it is done in the laboratory condition, not in a open environment. Okay. And then this so in the point of efficiency, it is a higher efficiency because the conventional PV panel efficiency is 30% only, but it gives 25.7%. Okay, it is almost 3/4 of the. And the tandem solar cells, the peroxides are integrated with the silicon. So I already told it is we can use peroxide as a separate material, or we can integrate with the silicon. Okay, so are other materials in the tandem configurations to surpass the efficiency limit of the single cycle solar cells. Okay. And the third advantages is stability enhancement. Means efforts are underway to improve the stability of peroxides under heat, moistures, and light. I already discussed. Okay. Addressing the concerns about this degradation over the time. Okay. The fourth one is the scalability. The current research focuses on the transition from a lab scale to large scale models. Okay. We can produce a compact or the large size PV panel to our requirement. Okay, by using the peroxide material. But in the if you are using the silicon material, it is a brittle one. We cannot fold it. Okay, so there is a major problem with the current commercial materials. So, which is innovations in the deposition technique and the roll-to-roll manufacturing process. Okay, this is so that only we can obtain the scalable product. Okay. And technique and the last one is environmental conservation. We already discussed. This is lead-free peroxide materials only preferred nowadays. Okay, if we are using lead peroxide materials, so we cannot reuse it, and also it is a toxic one. So this is a major problem. So nowadays the research is going on recycling strategies and addressing the toxic concerns. Okay. These are all the advancements in the peroxide materials. The challenges and the future direction of the pro- peroxide materials are stability and longevity. Okay. The stability and longevity is a major problem. Okay. Because this is developed by the minerals. Okay, so the addressing the degradation of peroxides under environmental conditions remaining the climatic change. So these, for example, light, moisture. So these parameters may degrade the materials of the composites. Okay, so the main challenges is stability and longevity. The second one is the toxicity lead-based peroxides. We already discussed in the last step. So the alternative tin-based peroxides are being explored to mitigate the environmental risk. Okay. So the if you are using lead minerals in the lead tin peroxide material, this is very toxic. The research is going on by for the recycling these lead and tin sets. Okay, and the scaling production. Okay, so this is a major thing. Okay, because nowadays uh, we are going to use the solar panels or solar cells in all the area. Okay, so even the mobile phone in future we can use the solar PV cells. or even the calculator we can use. So scalability is the main problem. Uh, in future, they can produce the micro solar cells. Okay, there's a possibility. There's a possibility. Okay. So the scalability production is a big challenges and the future of the ProX system. The overcoming the barriers in the scale of customer and defect-free large area power models is essential. And the last one is efficiency gains. That means the combining peroxides with other materials in tandem configurations offers a pathway to exceed 30% efficiency. Okay. And the last topic is application of peroxide materials. So we already discussed it is used in this building integrated photovoltaic plant. So, okay, the building integrated photovoltaic it is fixed in the outside of the wall, and we can use it as a PV window. Okay, and wearable and portable electronics. That means the lightweight and the flexible PSCs so can power portable device and wearable. Okay, so for portable and wearable device electronics, we can use this peroxide power. And third one is the agrivoltaics. Agrivoltaics means the tunable transparency algorithms. This means the greenhouse gases. The greenhouses. Okay, we can fix the peroxide material as a top layer. Okay, because it is a transparent one. Okay, it's a tunable transparent. So the tunable transparent allows the peroxide models to balance the light absorption because it is if it is in a transparent mean it allows the light to penetrate by through itself. Okay. For the electric generation and the plant growth green process. Okay. So it is the main applications of the PV panel. Okay. So the peroxide material is a we can conclude the peroxide material is a thin and transparent. Okay, and in the space application, so peroxides are lightweight and high efficient, so we can use in the satellite or the solar arrays in different areas. But the problem is the moisture and the light are degrade the material of the peroxide solar cells. So still the research is going on using the peroxide solar cells. So nobody's doing research in peroxide solar cells in India. Okay. So the last topic is a key drivers. This is the last topic. So the key drivers for the futures of peroxide solar triggers. So this one is efficiency improvement. Okay, so we can the PC has achieved power efficiency. You know very well. Okay, and the power PSC means the power conversion efficiency is 25.7% by the QCell company. But for the future potential is the tandem solar cells. Okay, it maybe give the efficiency up to 30%. Okay, and the advanced material engineering like the optimizing peroxide composition and the interfaces to minimize the recombination losses and enhance the light absorption. Okay. And the second one is the stability enhancement. So the current challenges in stability enhancement is the PSC. PSC means the power conservation efficiency degrade under the exposure to moisture, heat, and UV. Okay, so this is a degradation. There is a possibility for degradation. Okay, so the future solution for this problem is encapsulation techniques. So this is and this material can be encapsulated by any material or the composition environment. So the substitute of volatile organic compounds may be used in the with the peroxide solar cells or in the additive and passivation. That means the incorporation of stabilizing agents to mitigate the defect induced degradation. To mitigate the defects. Okay. And the third one is the scalability manufacturing. We already discussed. Okay, this is a big challenge. Okay, so this is a key driver. So so the current status, the lab scale production methods like a spin coating are not suitable for the mass production. So your roll-to-roll manufacturing process is the best suitable process. And the future approaches is roll-to-roll manufacturing inkjet printing, slot die coating, or integration with the existing infrastructure. This is the best future approaches instead of using the spin coating techniques. Nowadays, they are using spin coating techniques or blade split techniques. But the roll-to-roll manufacturing, inject printing, and the integration of existing infrastructure is a best future for this photovoltaic this toxic sources. And the cost competitiveness, the main advantage is lower material and manufacturing costs compared to the silicon solar cells, and the energy payback time is very low. Okay, so we can easily get back our investment. Okay. The future trend is reduction in the production cost through the simplified processing and increasing efficiency. Because not only selecting the minerals for the perovskite solar cells. Okay, the manufacturing technique is also a big challenge. Okay, and the last one is the sustainability. So the challenges in the sustainability is the lead-based perovskites. We already discussed it. It is a toxic one. It's a raise the environmental concerns. Okay. The future direction for the sustainability is they are going to develop the lead-free perovskites using the tin, bismuth, or antimony materials, and recycling the recovery methods for the perovskites models to mitigate environmental risks. Okay. Okay. So, in my conclusion, the perovskite solar cells represents a transformative technology in the field of renewable energy, offering the potential to achieve high efficiency, low cost solar power by addressing the challenges in the stability, scalability, and environmental impact. The perovskites can play a crucial role in the advancing solar energy adoption and controlling to global sustainability goals. Thank you. Do you have any queries? Manivel sir,
Sir,
and
yes, sir. There is some questions in the chat box. Sir, let's asking which test other than heat absorption are required for the developed material?
so can you ask something? Which?
Which other heat absorptions are required for the developed material?
Sorry, one second, one second. That's a call to me. Sir, heat.
Participant.
Sorry, sir. Okay, the call is so only I can listen your voice. So can you ask once again, sir? Heat.
1 minute.
The Manivel
Which
sir.
test other than heat absorptions required developed material?
So there is the thermal evaporation techniques is the best one, sir, because in the vacuum condition, so there is no possibility for degradation of the PV material. So that means the perovskite sources. Okay, so it also gives a uniformity of the uh, final material.
Other
Any other questions, sir?
one more person's raising the hands.
Yes, sir.
Check, sir. Suresh sir, do you have any queries, sir? You are raising the hands. Dear participants, this is the questionnaire sessions. If you have any queries, you can put it in the chat box, or you can directly ask with the resource persons. I think no more question with us, sir. Thank you for your wonderful presentations and most valuable points shared with us uh, to insight into leverage advanced manufacturing process uh, and produced thermal material that meet the evolving demand of modern applications, along with an phase change material, lightweight composite uh, through the uh, thermal materials and technologies. Real world applications in such as sectors of renewable energy and automotive systems also you elaborately explained. So we impressed and taken away of more valuable point from your sessions. This imperative to innovative and adapt to the thermal material to meet the growth technology for the current and future trends also we get through your presentation, sir. Thank you for your valuable presentations. Thank you once again, sir.
Thank you, sir. Once again, I thank Dr. Manivel sir and his team and the Department of Mechanical Engineering and the management of NPR College of Engineering and Technology for providing this opportunity. Thank you so much, sir.
Thank you, sir. Thank you.
So, shall I put my presentation, sir?
Yes, sir. Thank you, sir. Thank you.
Thank you so much.
Dear participants,